evening and welcome to class 8 of optimal design of tuning systems. So, in the last class, we saw about general stochastic optimization problems. We formulated a networking. Okay, so we we tried to formulate the mathematical model that is necessary to formulate the scheduling policy uh, to get optimal scheduling policies. So for that, we formulated two types of stochastic optimization problems, P1 and P2. And we didn't solve P1 and P2, we just wrote down the flow map of how to solve those two problems by using Lyapunov drift and Lyapunov optimization methods. So first step was we find points that satisfy the constraints. Then we construct virtual queues so that the constraints are met. Uh, Then we define the Lyapunov function, which indicates the network condition in the system. And if the condition is, if the Lyapunov function is high, the condition in the system is high, or you can come with a intuition that at least one of the queue is congested. If the Lyapunov function is low, then there is low congestion and mm, none of the queues are congested. Then we introduce the drift term. And uh, ideally, what you want to do is at each step you want to minimize the Lyapunov drift. Minimizing the Lyapunov drift pushes down the Lyapunov function, which intuitively decreases the conditioning system and makes the queue stable. Uh, but if you want to minimize an objective function, then you minimize a drift plus a penalty term. This penalty term depends on the objective function that you're trying to minimize. Yeah. So this is what we were discussing in the last class. But we did not discuss about the stability of a queue and what it means, what it mathematically means when we say that queues are stable. Right? So for that, we will start with queues. Okay, so since we are in discrete time, I'll introduce vector qt. This represents the contents of a single server discrete time queuing system. So this is the contents of single server discrete time queuing system. And here discrete time is defined over integers like time slots, t equal to 0, 1, 2, and so on. And the one assumption that we have is q of 0, the initial starting condition is greater than or equal to 0. So it's either positive or it is assumed to be 0. So basically it is assumed to be non-negative number. You could assume this to be also a random variable, but a non-negative number. That is right. The future states, um, like as time progresses, how does the queue evolve? Um, that is driven by your stochastic arrival and the server process. The stochastic arrivals are, so let's define the stochastic arrivals as AT, where AT is the amount of data has arrived in the system at time t. Uh, okay. Next, you have your server process. That is BT. This is amount of data that has been served at time t. Now the dynamic equation from Q can be written as Qt plus 1 equal to max of Qt minus Bt and 0 plus 8. So basically the amount of data in the queue or in the system at slot t plus 1 is equal to amount of data in the system at time t minus amount of data served in this time slot t plus amount arrived. So the amount that has arrived is added to the queue and the amount that has been served is subtracted. But if you subtract more than what is there, so this Qt minus Bt term, this can't be negative because you can't serve more than what is there. Hence, this max term Qt minus Bt comma 0. So we'll call this Qt as backlog on slot T. As a backlog at slot T. So this represents the amount of work that needs to be done, so that is still left to be done, right? And we have two stochastic processes, AT equal to 0 to infinity and BT equal to 0 to infinity. These are some sequences of real valued random variables defined over slots that integer numbers t. Right. The value of A represents the amount of new work that arrives at a time slot t, and that is assumed to be non-negative. So ATs are greater than or equal to 0 for all t. Uh, the value of BT represents the amount of work the server of the queue can process on slot t. For most of the physical queuing systems, BT will assume it to be non-negative, but you can come up with cases where we allow BT to take negative values. So we can allow BT to take negative values, and these values, these negative values, these would come up when we discuss about virtual queues. Okay, so now let us assume BT can be negative, right? Then you can modify the queue dynamics as seen in the equation. Well, I'll number this equation. This equation is blocked. You can modify one as you had t plus 1 equal to max q hat t minus beta t plus alpha t comma 0. Right. Here, what we have done is we have assumed at equals to 0 and bt is equal to beta t minus alpha t for all t. So you can modify one as this, but we'll use these type of equations that we have shown in one because we'll deal with multi-hop networks. Okay. And Because, okay, and now we are back to the equation 1. Equation 1 is 2t plus 1 equal to max of 2t plus, sorry, qt minus bt, comma 0 plus 8. Okay. Okay. So q0 is greater than or equal to 0, right? And 8t is also greater than or equal to 0. Because q0 is greater than or equal to 0 and 8 is greater than or equal to 1. And this term would always be greater than or equal to 0 from the definition. Q t plus 1 also is greater than or equal to 0 for all t belongs to 1, 2, and so on. Since this is greater than or equal to 0, all the backlog is greater than or equal to 0 for all starts t. The units, so the units of qt, at, and bt. Basically, these are the three variables that we're working with. One is the backlog, arrivals, and service. These depend on your network system. Right. In a communication system with fixed size data packets, these quantities might be integers with units of packets, or they could be real numbers with units of bits, kilobytes, or some other unit of work that is relevant to that system. Doesn't matter. Yeah, we can rewrite again. We can rewrite equation 1 as 2t plus 1 equal to qt minus b hat plus 8, where b hat t or b tilde t is the actual work processed on slot t, which may be less than the offered amount bt. If there is little or no backlog in the slot t, then b tilde t would be always less than bt. So bt is basically what is the amount of packets you can serve in that time slot t. B tilde t is the actual amount of packets that you have served in the time slot. So B tilde t is defined as it is the min of either the total amount of service that you have proposed or the total amount of that is remaining back. And from the definition of this, we can see that B tilde t is less than or equal to bt. Right? So now using all these, we will describe a lemma. This lemma is the sample path property. So for any discrete time fuel system described by one, and for any time slots T1 and T2 such that 0 less than equal to T1 less than equal to T2, we have the equation the backlog at T2 minus backlog at T1 is basically telescopic sum sorry. T1 T2 minus 1 the arrival process minus the actual amount that you have to insert B tilde. And from here, so this is the first claim. And the second claim is for any t greater than 0, we have qt by t minus q0 by 0 is equal to 1 by t summation t equal to 0 to 3 minus 1 arrival process minus 1 by t summation t equal to 0 to t minus 1 b tilde tau. This is the second uh, hypothesis. And then we have similarly q3 by t minus q0 by t greater than or equal to 1 by t summation tau equal to 0 to t minus 1 a tau. Beta. Now, this is the amount of service that has been offered, not the real amount of service that has been done. Okay. We'll use this second equation. I will number this as P. Using Q, right, we have Q t plus 1 minus Q t equal to A. Okay, I'll write it down for tau. Q tau plus 1 minus Q tau equal to A tau minus A tau. And we will take tau belongs to P1 to P2 minus 1. Right? So if you sum it over, tau equal to P1 to P2 minus 1, Q tau plus 1 minus Q tau equal to summation tau equal to P1 to P2 minus 1, P tau minus B tilde tau. So this term on the left hand side is basically a telescopic sum that we have defined in the last class. This is equal to the first term Q G, the last term minus the first term, right? And this is equal to summation tau equal to T1 T2 minus 1 A tau minus summation tau equal to T1 to T2 minus 1 B tilde. This is your first proof that is been done. Okay. Next, you just replace T2 equal to T and T1 equal to 0. And you get second equation and divide by T. You get the T equation Qt2 by T minus Qt1 by T. 1 by T summation tau equal to T1 T2 minus 1 A tau. Tau equal to T1 T2 minus 1 B tilde tau. And using the inequality, this from definition, this third inequality, we get this term Qt by T minus Q0 by T is greater than or equal to summation tau equal to 0 to T minus 1 A tau minus 1 by T summation tau equal to 0 to T minus 1 B tau. So here this is your arrival process. This is your arrival process. This is your departure process, service process. Okay. So we have the proof for this line, the sample path property. So one of the important application of this lemma is it shows that we'll see. Okay, so the important application is limit t tends to infinity ut by t. This tends to 0 if and only if the time averages of your arrivals minus departure. This tends to 0. So your the total amount of service, total amount of work done as limit t tends to infinity should be equal to the total amount of work that is being arrived. Then you can say that my queues would tend to the queue lengths or the backlog amount of work that I have that tends to zero. Right. So the time average of 80 minus B tilde T, where B tilde T is the amount of work that you have actually done, not the amount of work you can do. And if you replace it with BT, the amount of work you can do, then it will become an inequality. Right. So the amount of work you can do should actually be greater than the amount of work that has happened. If that satisfies, then you can say that the Q is less than, it will not blow up, it will be stable. So this actually motivates the two definitions of Q stability. One is the rate stability, and the second is mean rate stability. I'll define what rate stability means. So rate stability theory. Okay, so first the definition. Rate stability means any discrete process as defined by the equation 1, Qt, is rate stable if limit t tends to infinity, Qt by t is equal to 0 with probability 1. So if the limit Qt by t tends to 0, then it's known as rate stable. Okay, and we have mean rate stability. This is Qt is mean rate stable. The limit of expectation of the Q is equal to 0. Next is a theorem. This theorem is about rate stability theorem. Suppose Qt evolves according to equation 1 with AT greater than or equal to 0 for all t and BT some real value for all t. The time averages are finite constants. So if you have limit t tends to infinity 1 by 2, summation I equal to 0 to t minus 1 AI. This is AAB with probability 1. Limit t tends to infinity 1 by t summation I equal to 0 to t minus 1 BI. This is your BA with probability 1. Then the QT is rate stable if and only if AAV is less than or equal to BAV. B. If AAV is greater than BAV, then limit t tends to infinity QT by t is equal to AAV minus BAV. Okay. So the A part will prove the A part. So suppose Qt is rate stable, right? This implies limit t tends to infinity Qt by equal to 0. Then we'll use this C. Qt minus Q0 by 0 is greater than or equal to 1 by t tau equal to 0 to t minus 1 a tau minus 1 by t summation tau equal to 0 to t minus 1 beta. Now we take limit on both sides. Limit t tends to infinity Qt by t minus limit t tends to infinity Q0 by 0 equal to. Okay. And we can see that this is greater than or equal to limit t tends to infinity Qt by t because this is a positive number. So this will always be greater than this because we're subtracting an equation from here. And then from the hypothesis we have, these two have limits and they are a, b, and s, a, b. This is limit t tends to infinity Qt by t. But then this is equal to 0 from the rate stable condition. Therefore, 0 greater than or equal to AAB minus BAB, which implies AAB is less than or equal to BAB. So we have proved one way. The other way is if AAB is less than or equal to BAB, we assume this, which implies AAB minus BAB is less than or equal to 0. Right? We also have this quality. So from this we have A, this B. Relation between A and B is so here we have to use the P tilde. From the definition of B tilde, we have P tilde T is less than or equal to P, right? So we have let limit P tends to infinity 1 by T summation tau equal to 0 to P minus 1. B tilde sorry, B tilde A. So from this inequality we have B tilde AB is less than or equal to B. Yes, minus B tilde AB they are equal to minus B. AB minus B tilde AB is equal to AB minus BA. Okay, and this is equal to Q. This is QAB. So QAB is greater than or equal to AB minus BAB. So QAB is basically sandwiched between two zeros, hence QAB would tend to 0, right? This is the proof of reachability. Specifically, reachability says that if QT is reachable, then the average arrival rate is less than or equal to average rate that you can service. And if average arrival rate is greater than DAB, then limit QT by T is equal to AB minus BA. Next time, define another theorem which says the necessary condition for rate stability. Suppose QT evolves according to 1. With any general process AT and BT that can be defined before, says that AT is greater than or equal to 0 for all T. Right. Then if UT is rate stable, this implies lim sweep 1 by T summation tau equal to 0 to T minus 1. A tau minus B tau is less than or equal to 0 with probability 1. B, if QT is mean rate stable and expectation of Q0 is finite, then lim these two parts you can see directly follow from equation 1. If we take lim sup on both sides, and noting that qt by t tends to 0 as qt is reactable, we get a. And similarly, by taking expectation on both sides, and similarly noting qt by t tends to 0 as qt is stable, gives you the second. You use here two properties of expectation. One is monotonicity and linearity. Of stability. So the rate stability and mean rate stability only describe the long-term average of arrivals and departures. We can't say anything about the fraction of time the backlog exceeds a certain value or about the time average expected backlog. We can't say anything about that. The stronger stability conditions that if we want to apply across our system, then we can use different stability conditions. One is the steady state stability. So steady state stability. A discrete process Qt is steady state stable if limit m tends to infinity gm equal to 0, where for each m greater than or equal to 0, this gm is defined as lim sup p tends to infinity 1 by summation tau equal to 0 to t minus 1 probability of your fuel at time t being greater than m. So basically what physically this means is the probability that your Q exceeds a threshold M goes to 0 as M increases to infinity. So the probability that your Q exceeds a very large number is basically 0. So this gives you the condition that your Q's don't belong. Similarly, we have one more condition of stability, that is strongly stable. Lim sup t tends to infinity 1 by t summation all equal to 0 to t minus 1 expectation on u tau is finite. Under this mild boundedness assumption, strong stability implies all of the other forms of stability. Right. Oh, the Markov decision processes where your current state of the system is a function of your previous state, the control action that you have taken in the previous state, yeah, and some randomness in the system. Right. And if you see the Q equation that we have defined in for one, your current state is a function of the previous state and the control action and some randomness. So this is your previous state. This is your control action. This is the randomness in the system. So the queuing theory has some significance, some relations with the DTMCs, where DTMC are discrete time Markov chains. So if your QT is defined over an ergodic DTMC with finite or countably infinite state space with a finite or countably infinite state space, and with the property that for each value of m, you denote an event such that your Q is always bounded by n. This corresponds to only a finite number of states in the steady state. This implies steady state stability. So this implies steady state stability and the existence of a steady state distribution in your DTMs. Strong stability implies that there is a finite average backlog, and then you can use it to theorems to find the finite average delay. But even with the strong stability and steady state stability, you are able to find average metrics in your given system for ergodic DTMC process. The rate stability theorem that we have discussed are the simple methods for stabilizing IGQ network. And using the rate stability theorem, we can make scheduling decisions so that the time average of service that you can provide and the arrival rates uh, are well defined. And if you have a queue with less arrival rate average and more service rate average, then that QI would be stable, right? So with the knowledge of the arrival and the channel properties, you can find out uh, a way to serve different processes so that the desired time average can be achieved so that your queue doesn't blow up, right? Uh, yeah, so we'll do an example today, and then the next class also we'll do one more example. So first example we'll do is a 3Q 2 server example. So consider a 3Q 2 server system. What does it mean is you have three queues, each with backlogs of Q1, Q2, and Q3. And then you have arrivals A1, A2, A3, but you only have two servers, right? There are three queues and two servers. At each time, you can make a decision of serving two of these. The base assumption is all packets have fixed length and the queue is allocated to a server on a given slot and can serve exactly one packet on each slot, right? So we choose at every slot, time slot, we choose which two queues to serve. So PIT is one if server is connected to queue. I at slot T, zero otherwise. Assume the arrival processes are A1, AB, A2, AB, and A3, AB. These are well-defined averages. So we'll design a service allocation algorithm to make all the queues rate stable when the arrival rates are A1, A1, AB, A2, AB, A3, AB. This is 0.5, comma 0.5, comma 0.9. So what do we need to choose? We need to choose B1, P, B2P, and B3T at each time, right? To be, we need to choose this, and they need to be IID and every slot. And you can choose such that only both of them are 1. 3 of them can't be 0. So these can take the values 0, 1, 1, 1, 0, 1, 1, 1, 0. Yeah, this could also be 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0. Yeah, but we'll not use these because whenever you want to sum as more as possible, right? So we have the choice to 3 of the vectors 0, 1, 1, 1, 0, 1, 1, 1, 0. So now from these error properties, you can see that the third has the most number of arrivals, 0.9 average. 0.9 average, the A3B arrives. So we want to choose between these two. So if we choose at each time t with probability 0.5, you either serve 0, 1, 1, or with probability 0.5, you serve 1, 0. Then you can see that B1 average, comma B2 average, comma B3 average. This is zero point 0.5, zero point 0.5, and 1. And this satisfies this condition we saw in the rate stability theorem. AB is less than or equal to AB. This implies that the QT is rate stable, right? So one way of designing the scheduler is to choose 0, 1, 1 and 1, 0, 1 with probabilities 0.5. And we get your service average is 0.4, 0.51, and clearly AI average is less than or equal to BA average. So the rate stability ensures that the QS are stable. This is a randomized scheduling algorithm. One could also design a deterministic algorithm by saying that okay, actually, if every even time I choose this, at odd time I choose this. But then the rate stability theorem makes sure that my Qs are stable. Okay. So the next one, A1 AB, B1 AB, sorry, A2 AB, A3 AB is 2 by 3, 2 by 3, 2 by 3. Now, since you have choice between these three, you can choose equally. With probability 1 by 3, you choose 0, 1, 1. Probability 1 by 3, you choose 1, 0, 1. The probability 1 by 3, you choose 1, 1, 0. And you get B1 AB, B2 AB, and B3 AB as 1 by 3, 1 by 3, 2 by 3, 1 by 3, 1 by 3, 2 by 3, 2 by 3. You can also choose the deterministic counterpart of this where you say that at each you can have your whole real number and then say that okay, first time I choose 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Periodically you change 0, 1, 1, 1, 0, 1, 1, 1, 0 periodically. This will also make sure that the the rate theorem stability theorem will make sure that your Qs are stable because your B1 AB are greater than or equal to A1. Okay. Now one last example. A1 average, A2 average, A3 average. This is 0 0.7, 0 0.9, 0.4. Okay, so basically what you want is you want to find three probabilities to choose from these three things. So you have P1 with probability 0, 1, 1 plus P2 with probability 0, the state 1, 0, 1 with probability P2 plus with probability P3, you choose the state 1, 1, 0. This should be greater than or equal to 0.7, 0.9, 0.4, and P1 plus P2 plus P3 should be 1, and Pi should be greater than 0. So this type of formulation is basically a linear program. So for today, I'll just write down the unique solution that I see here is P1 is 0.3, P2 is 0.1, and P3 is 0.6. And now from these, we can write V1AB as P2 plus P3. This is 0.7. B2AB as P1 plus P3, and B3AB as P1 plus P2. This is 0.9, and this is point this is 0.4, and this is 0.9. Yeah. So you have these equal to A1, AB, A2, AB, A3. Hence, from the reachability theorem, we can say that these Qs should be stable. So yeah, that is for today. We'll discuss more about reachability theorem with one more example in the next class, and then we'll go to dynamic scheduling examples where basically we are trying to come up with scheduling policies so that your queues are stabilized.